Okay, so one of the main things that we can do, now that we can take derivatives of inverses, and now that we can do implicit differentiation, is we can start taking derivatives of things in a slightly easier way by first making things harder for ourselves. So here's something we haven't taken the derivative of yet, and it's because we've been sort of afraid of it, but let's take the derivative of log of x base a. Now, instead of taking the derivative of log of x base a, we're going to replace y equals log a of x with x equals a to the y. Remember, that's the definition of log a of x was that x equals a to the y. And so what we're going to do is we're going to take the derivative of this equation by using implicit differentiation. So we're going to take the derivative of x, and we're going to take the derivative of a to the y. Well, the derivative of x is just 1, and the derivative of a to the y is a to the y ln a times y prime. Now, it's real easy. We're just going to solve for y prime by dividing both sides by a to the y ln a. So here we've got an expression for y prime. And do you remember what a to the y was? It was x. And so it's just 1 over x times the natural log of a. So that's really nice. The derivative of log of x is 1 over x ln the base. If the base is e, instead of writing log, we write natural log, ln, and so the derivative of ln of x is just 1 over x. Why? Because the ln of e is 1. So, how about the chain rule? What's the derivative of log of a function? Well, it's just 1 over f of x, right? Because the derivative of log is 1 over the input, times f prime of x. And written nicely, it's just f prime of x over f of x. And so, let's use the chain rule to let's start trying to prove some things. So we have, say, y equals x to the n. If I take log of both sides, what do I get? I get ln y equals n ln x. If I try to take the derivative of both sides, I'm going to use the chain rule on the left and get y prime over y. And on the right, I'm going to get, well, it's n ln x. N's just a constant, so I get n times the derivative of ln x. The derivative of ln x is x prime over x, and x prime over x is just 1 over x. And so I get y prime over y equals n over x. And that means that y prime, if I multiply both sides by y, is y times n over x, and y was x to the n. And so I get x to the n times n divided by x. And x to the n over x, well, that's just nx's, take away 1, so I can write that as nx to the n minus 1. You know this already. We know the derivative of x to the n, and I promised that we would come back and prove it sometime, and now we have. We've proved that the derivative of x to the n is nx to the n minus 1. Alright, so let's take the derivative of another familiar function, tangent. We're going to write tangent as a quotient, so we're going to write tangent as sine over cosine. And we know the answer is secant squared, and we don't care about that. That's not the important part. What we're going to do is we're going to try taking log of both sides. So log of y is log of sine over cosine. And remember, logarithms take subtractions and change them into, take divisions and change them into subtractions. So I have ln y is ln of sine minus ln of cosine. So let's take the derivative of all of this. Well, I get y prime over y equals sine prime over sine minus cosine prime over cosine, which is cosine over sine minus negative sine over cosine. I can change those two negatives to a positive, and then cosine over sine needs to be over sine cosine, and sine over cosine needs to be over sine cosine so that I can add those. And so I get cosine squared on the left and I get sine squared on the right, and then I can finally add because I have the same denominator, but cosine squared plus sine squared is 1. So I get 1 over sine x cosine x. Now that's y prime over y. So I need to multiply 1 over sine x cosine x times y. And what was y? Y was sine over cosine. My sines cancel, and I just have 1 over cosine times cosine. And that's secant squared. So we got the derivative of tangent is secant squared by using logarithmic differentiation. It checks out. So the process of taking the logarithm of both sides before taking the derivative is known as logarithmic differentiation. It's absolutely most useful when we try to take the derivative of complicated products and quotients. Look at that terrible thing that we're trying to take the derivative of. In the bottom, we have a product. In the top, we have a product. We have a quotient overall. We have powers everywhere. But if I was to take the logarithm of that, it would split into just a bunch of sums and differences, right? The products on the top are my positive values. The products in my bottom are negative values. Powers become coefficients. And then the only thing you have to do, remember the derivative of log of something is y prime over y. And so at the end, you have to multiply by y again, which is why this extra term is showing up over here. But believe me, taking the derivative of a bunch of sums and subtractions is way easier than taking the derivative of a bunch of products and quotients. So let's use that to take this complicated derivative. What's the derivative of x cubed sine x over e to the x? First take log of both sides. We get ln y equals ln x cubed plus ln sine x minus ln e to the x. Now two of these simplify. Log takes powers and makes them coefficients, so we get 3 ln x plus ln sine x. And the log of e to the x, since log and e to the x are inverses, we just get x. So when we take the derivative, we get 3 over x plus the derivative of sine over sine minus 1, and that equals y prime over y. So y prime is y times 3 over x plus cosine over sine minus 1. And so we just plug y back in, and we multiply by the thing we just took the derivative of. And I promise you that this was much simpler than using the quotient rule and the product rule and then simplifying. So go ahead, practice taking some derivatives by using logarithmic differentiation, and I'll see you next video.